Okay, dear colleagues, let us slowly start. And today we have AI seminar at TI, and it's my great pleasure to have today Alexey Zaitsev, who is assistant professor at Skoltech Moscow and also visiting research fellow at BIMSA Beijing. And Alexey holds his PhD in applied mathematics from Institute of Information Transmission Problems in Moscow, and his research focuses on developing new techniques for sequential data, enhancing robustness of deep learning models. And Alexey has, extensive publication record, including conferences like KDD, ISTATS, ACM Multimedia, and also he has many works in applications, especially including banking and oil and gas industries. So, I think we are good to go. So, Alexey, the floor is yours. Please start. And the topic of presentation today is processing of event sequences via neural networks-based models.
Okay, thank you a lot, Maxim, for invitation to this seminar. And today, yes, I'm going to talk about how neural networks can be used to process event sequences data. And shortly, you will know what this event sequences data and so on. A small introduction slide on my research and publications. As you can see, a typical profile for artificial intelligence researcher these days is some good publications at ISTATS, KDD, and so on. I'm now like 6 years past my PhD defense, and my research interests a bit shifted. Actually, my PhD was on some specific theoretical/practical results for Gaussian cross regression. Now I'm doing this, but not often. I'm more interested in industrial application of deep learning. And if we are talking about fundamental science, it's about processing of sequential data of various kinds and examining the reliability of deep learning models, adversarial attacks, robust deep learning models, and so on. You can see some companies I have joint publications with, and some my collaborators, and so on. And let's dive deeper into the lecture itself, because about me, you can read on my site and so on. What I'm going to talk to you is to represent on how we can do representation learning for event sequences and how this approach is different from other approaches, and these models are different from other models, and how this approach kind of joins neural networks with fundamental theory on temporal point process, what a thought approaches is doing now. And if you have questions, it's okay to ask these questions at any time. So I'm most welcome to do this. So let's start with intro of what are event sequences and what kind of models we can try to apply to them. So this is a simple example of an event sequence. One of my days, I'm working in academia, and I exhibit a series of events. And actually, a bank, I have a card date, has a data on these events, that I reviewed at some moment, then I get a lunch, transfer some money. Also, there can be events of other types, like log into a bank application or watch some movie in the evening. So overall, we have a series of events, and we can have features specific to each event. In the most common case, we say that we have times of these events and some features of each event, which can be some numerical features, like how much money I spent or the allocation, or some more complex features like what message I sent at a particular time in some message app, like WhatsApp, WeChat. So we want to introduce a model to this events, and what I want to emphasize now and then is that the distribution of events in time is typically non-uniform, and this distribution is quite important to identify some important things on this series of events. For example, if you have some very strange money transfer in the night, it can be a signal of an anomaly or a fraud. Or if you see that we have a series of very close events that are not typical for, I don't know, for weekend, and it's more typical to working busy days, it also can be a sign that something has changed in the life, and we want to make some conclusions from this. And actually, we encounter this type of data in many stations. There are some stations on this as a slide, and you can see that there are a clickstream of data when a user visits internet and visits a lot of sites, and for each site he watches or she watches a lot of videos, and each watch is a particular series, a particular event we want to deal with. One of the most popular application of this type of models were financial trading, because of flexibility on that we can try to collect information from many events and, for example, predict prices or predict volatility for this time series. Another quite recent application, and a lot of articles were devoted to the problem of disease dynamics, given the recent spark of the interest due to COVID-19. In this case, we also can say that each transfer of a disease is an event, and each new illness is an event, and we are interested in analyzing of development of this disease, of spread of the disease, and on how can we control the spread of the disease and what measures play an important role in this case. And I'm mostly working on this last topic, kind of a subset of the general framework of event sequences related to financial transactions. And we want to collect some idea of what and when user spends his or her money, and we want to make a model on top of this. Okay, well, it's kind of the most simplest approach that can try to capture the dynamic. It's just to say, let's say it's a time series. So we can say that, okay, for time series, we have a uniform distribution of our observations. For example, we measure temperature each second. Here, the events are discrete, but we can try what we can try to do to pay attention to the non-uniformity of this data. We can try to split the data to some epochs or to some subseries, aggregate events in each epoch, and say that now we have this common time series. For example, we have events for each day, and using a bag-of-word approach, we can collect all types, and we have a kind of good representation. But actually, this approach provides a model, but as well, it raises a lot of questions. For example, how long should be each epoch? Because if the epoch is too small, then we will have a lot of epochs with no events, and it leads that our model works in a quite strange way. Another question is, how should we aggregate events per epoch? This also has some obvious answer, like let's cover this label encoding and put the number for each epoch, for each type of event that equals to the number of events of this type in each epoch. But you feel that there is some limitations. We don't take into account, for example, the time of the particular event inside the epoch. So we definitely lose something. Also, what if there are no events in one epoch? How should we proceed? And last but not the least, this split allows only for limited understanding of what is going on and limited modeling. For example, it's very hard to say from such aggregation on the distribution of the type and time of the next event, how and when something new occurs. Because in this case, we have a block, and we can say that something happened in this block that's related to a particular epoch, and it's not what we want because but we can say that even if you do this type of approach right, you get some benefit. For example, as a slide, you can see a work by our colleagues from a major Russian bank that is they were developing an approach on how should we proceed this series of events as just a sequence of events without taking into account uniformity. And even in this case, when we use this variant of recurrent neural network with a proper reprocessing of events, we obtain higher Hope values for the famous credit scoring problem. And the improvement is significant given that the source of the data is the same and we limit our recurrent neural network to a small number of features compared to logistic regression and a variant of gradient boosting LGBM. Because in this case, with a proper treatment, with a proper neural network, we can do an improvement. But we can do even better when we impose a good model. And to deal with this model, I need some formalism. It is not very hard, but it is different from what you are typically dealing with different types. Okay, so suppose we have a series of events. We suppose they are of this single type now, but we can say that okay, it's also a random process. So you can see this time scale, and we have events at time t1, t2, and t3, and in total we have a history H capital of events. And in this case, we see that okay, it's different from, for example, Gaussian process. The nature of this process is discrete, and typically we deal with the random process with the value at a particular point for the realization of this process being the number of events that happened before the time t. For example, at this time t on this slide, we have n of t that equals to 3. And in general, we can formally say that it's an integral differential, this random process, NS. And also we can say that we just sum up over all events in our history, and the sum we sum in this case delta functions. And this is a formalism, and it can have pretty simple and I suppose familiar for most of your applications. For example, it can be a Poisson process. In this case, we can say that the events occur randomly, but with a constant intensity. The average number of events at the unit time is the same and equals to the constant mu. And really many real-life processes can be modeled as a Poisson process. So we can say that if we feel that it's okay to for example, okay, some independence in history, some property of uniform random occurrence, and so on, then we have this Poisson process. And many real-life processes like number of people in a queue or kind of other mass-serving processes are kind of similar to this. people that are coming to bus terminal, people that are going by metro, and so on. And it's kind of simple model, and it allows a simple inference, a simple estimation of the parameter mu. But for sure, in real life, we have something more complex. And in general, we're interested in more detailed thing, in the complex distribution of the next event time and the next event type. So we can say that we can model this in the following way. By the way, thank you. This picture and many other nice pictures in this tutorial are taken from ICML tutorial on event sequences as temporal point process. You can find them. I don't have enough time to cover all the things that are part of this big field, but I can go with a part of it. So if you want to get more details, you are welcome to look into this tutorial. So what we are looking at, we have events at time t1, t2, and t3, and then we want to somehow model the conditional distribution of the next event time. We have a single type of the event, and we are interested in the density, conditional density of the event, given the history before this event, this f star. Also, we can say that to have a probability for an event to happen from t to t plus dt, the probability is f star t times dt. And also, we can define S star capital here. It is the probability that an event is happening not before the time moment t. This is the area on the red part of the curve, this red area we want to compute. And so if we have density, and if we have the probability, this S star probability of event not happening before t, we can formally write down the likelihood for this event sequence. It would be the product of the densities at the times of events t1, t2, t3, and t, and this probability that nothing is happening after t until the end of our observation time t capital. So it's pretty nice form, but in this area, typically we use another form of the likelihood. We, instead of densities and S star, introduce the intensity. Intensity is the conditional mean number of events conditional on the history. Formally, we can prove that we can get intensity as the ratio between F star and S star. And because of this, we can rewrite the likelihood in the following form. It would be the product of intensities and exponential of the integral of the intensity from 0 to t capital. It is a good thing because right now it's enough to specify the parametric form of lambda star. And if you have some parameter, for example, W, we can optimize them by maximizing the likelihood. Bad news is that we have an integral we want to compute here, but this integral is pretty simple because it is a one-dimensional integral. So we can easily say that let's have some simple Monte Carlo one-dimensional integration. And if you have this kind of approximation, we now can write down and compute the likelihood and maximize it. For Poisson process, we have an analytical solution. For more complex processes, the question is more different. In particular, we are often interested in the effect called self-excitement. What does it mean? It means that now we have more complex dynamics. of the temporal current process of this random process of events. And we have, for example, a self-excitement type of dependence. That means that the intensity jumps up each time we observe an event, and then it gradually decreases to this constant level. Formally, we can say that our intensity, lambda star, has the following form. It has some basic intensity, mu. Then we add the intensity increase due to past events. So we define some kernel function that is the function of the difference between the current type and some event time in the past. For example, it can be something exponentially decreasing, and some this bonus intensity over all the events for this particular time. So for each event, ith event, we calculate the value of this kernel function, and we get the resultant intensity. Typically, the kernel is such that it decreases as the difference between T and Ti getting bigger and bigger. And it means that at sometimes you have no effect on the intensity from the past events because they were all far away from the present. And we have only the basic intensity left. This model is quite natural, for example, for disease spread. Because if you have more and more people that can transfer the disease in a city, it is higher, the probability to transfer the disease is higher. And because of this model kind of is very popular in this area. And this is some example of the real life modeling of this type of self-excitement in the below right corner. And actually, it's also very often encountered in finance. So this is one famous example of such process. It's named after Alan Hawkes, who invented this process back in 70s. Okay, he didn't become a star in this era, but his works were discovered in the beginning of 21st century. And now he's given a lot of talks about his invention that dates back to 1970s. So, okay, there are other examples that you should know about. And this kind of typical modern application is to construct a combination of these ideas. So we covered a simpler Poisson process with a constant intensity. We also considered self-excitement point process, where we have excitement due to past events. Also, two good examples are a homogeneous Poisson process. In this case, the intensity does not depend on the past events, but it has some complex form. For example, it can have some month periodicity. And in this case, we have this function g of t, that's intensity. Also, another example of point processes widely used in applications is terminating point processes that ends at some point. You can imagine that this type of process can be used in insurance because the main problem in insurance is to understand what is the probability of something to break, and not only the probability, but the probability distribution with the times of particular thing happening. For example, it can be car insurance, and we're interested for a particular person, what is the probability for him to encounter a road accident? Okay, in the next part of the talk, I will mostly focus on Hawks or self-exciting point processes and on how can we model this process with neural networks. But before, I want to make two additional notes on what are the effects and what other ideas are there in this area. The first idea is to have more complex dynamics if we have many people to embed the graph structure in this point process. And it's called mutually exciting point process. When, for example, Christine and affects Bob. So if you have some event for Christine, the intensity of the events for Bob is increasing. I don't know, maybe it can. Some events are visiting a doctor or whatever. Anyway, you can see that the formula is pretty close to what we have seen before. We just add another term that is related to effect of Christine's past events on the intensity of what's happening to Bob. And another example is market temporal point process. And I would say that almost all random processes, temporal point processes, are related to this marked temporal point process type. The idea is to equip each event with some mark. It can be some categorical variable, or it can be a list of features. And it's very natural to look not only at what time something's happening, but what exactly is happening. For example, we have a random process of traveling from Atlanta to Savannah, and we want to understand when a car will need to refuel the gas, or when but a passenger will need to refuel him or herself in McDonald's. In this case, we are interested not only in that something will happen at stop, but also what type of stop we'll encounter, for example, to target some advertising very closely to what the person would like to do. And so, what is the main approaches here for modeling event sequences? We can stay on the left side and say that we have a sequence of tokens as, maybe with some features if we have marked temporal point process. And we can model them with common recurrent neural network or transformer or convolutional neural network. And it can be a good approach, but it drops some ideas from the data. Some part of the data is just dropped, so it can be perfect. It assumes a uniform time of events. We can try to overcome this difficulty by imposing positional encoding, but typically it's not enough. Also, I can say that we can apply self-supervised approach here. For example, borrowed from NLP-Word when we want to try to predict the next token. And we can say, okay, tokens and events, what's the difference? They are both some points at time scale. So let's, for example, try to predict this next token or next event. And overall, we have a model that will be able to predict the next event. And we are pretty sure that this model will also have some representation capabilities. If we pass to a neural network model a series of events, we will have, after processing, some meaningful representation. This representation reflects on what in this sequence. So we go this way and adopt all tools from natural language processing. They are pretty easy to adopt, and this RT-RNN models of this family. In this case, we typically have faster inference and faster training. In a way, it is more user-friendly approach because it doesn't impose complex likelihoods. we can define and optimize something simpler, but whatever. What is, in my opinion, more interesting approach is temporal point process approach. In this case, we assume that we have some non-uniformity of the data. It's internal non-uniformity. And so, as it is incorporated in the model, it should provide better results in some problems related to prediction of the next event type or prediction of the next event time. In this case, we also can say that we don't need any supervision. If we have a sequence of events with marks or labels for each event, we can also define particularly this self-supervised approach. And you can see that in this likelihood, we don't need the labels. So I would say that this is another type of self-supervised approach, but more principled. There are some tools for temporal point processing modeling, and we will cover some of them later. And they would be able to model all these types of behavior with terminating, with self-excitement, and so on. And this is kind of important thing. And because of this, I believe, and it holds, I will see some results in the end, that we will have a better models for applications. So what is the difference between non-narrow and narrow Hawkes processes? Let's start with the figure. So each yellow point here is an event. And for these events, we have types. In this case, we have two types of events, this violet type and green type. And we have intensities associated with each type of event. So we have intensities related to the event of the first type and intensities related to the event of the second type. And you can see that in this way, we can model quite kind of complex dynamics with self-excitement and even the effect when the intensity of the event decreases after the event of other type. And this is possible because we have a more interesting model for the intensity. And you can see that here, these yellow dots are not just events, they are LSTM units. So we can start with some very basic, just saying that we will have an LSTM block or a token for a transformer. In this way, we will be able to model these intensities. But in this case, we have again this discrete nature of the data, and we don't know what is happening between two events. And because of this, it's not a very good model now. But the authors of this article introduced on how can we model the intensity for time intervals between the events. They say, let's have some representation, and this representation would be a function of actually two representations. But for now, we can say that we can calculate this RT at the moment of each event. So I say that we define R of t as an output of classic LSTM. And then we can say that the intensity is a single fully connected layer. So if this R representation is a vector, then multiply it by the vector of parameters WU transpose to have a single number and apply some activation function, for example, exponential for the intensity to be positive. Okay, so this is possible when R is a function we can calculate at each time moment. How we do this? We say that we start with two cell states actually. And we recalculate this at each event. The C with a line and C without a line. So we have this Ci plus 1 after an event and Ci plus 1 with a bar after an event. Also, we have a vector of parameters delta, and we calculate C of t, a continuous cell state, in the following way. So it has some basic vector C bar I plus 1 at each time moment, plus the second term that equals to the difference between these two vectors if t equals to ti. So in this case, we start with Ci plus 1 at time point ti, and then we go continuously to the cell state C bar I plus 1. And the dynamic is governed by this exponential function. So if you exponential decrease on the effect of this first immediate cell state, and we slowly move to this infinity cell state. If we have this continuous function C of t defined, we can define the representation in the following way, just a nonlinear transformation. Ct with an additional vector, or I here, that's also output of an Ernen block. And now we can define the intensity function. And because of this, we are able to define this temporal point process and calculate event time at each time moment. Okay. So there is another work, not surprising, based on transformers that adopts the similar idea. But in this work, we try to get these representations from HT. So from a transformer no model with attention, we calculate attention between events, and now we have representations at each time point, and also to define intensity at some point between two events, we have this formula in the bottom part of the slide. In this case, we have again some actually close to exponential decrease that starts with some base intensity at the event and the representation of the event in time j, and then we have this dynamics defined. If we have intensity, we can calculate the conditional density and say that the mean time to the next event is the expectation, yes, with respect to this conditional intensity. And the next event type is just the maximum with respect to all intensities we have, as a maximum argmax with respect to k for all k if you have k different types. And you can see that we have a different dynamics for each event time governed by this vector of parameters specific to this event type k. So it's pretty simple addition to a transformer model, but okay, it was published at the right place, at the right time, and now can be used. What we mentioned, actually, what we see here is that we can try to use also convolutional neural networks of point processes. This is what we have been doing. And the difference between other works and our work on convolutional neural networks for time series processing is that we define not this finite support kind of kernel with few parameters. We define a complete convolution, and we say that we apply this convolution function to this intensity function, and in this way we take into account non-uniformity of the events in a sequence. And because of this, we have this continuous convolutional layer, never introduced before. And if we want to predict the next time of the event, the next type of the event, or the intensity, we can have it like this. So again, we have this convolution that results in the representation at each time point ht. We have a specific convolution that allows us to get the intensity in the future. You can see the formula here. Okay, I suppose the main, thank you, Evgeny, for the question. I suppose that the main difference between this approach and many other exponential recommendation system approaches is that right now we have a specific likelihood function that is tailored to the problem itself, that is just not some heuristic loss function. And that because of this, we can have a principled prediction of the next event type as next event time. So I would say that it's a better approach from statistical point of view. And in applications, we often see the similar thing, that if you take it right, we have some improvement over simpler approaches. But I agree that many works in recommender systems tries to do some kind of sequential recommendations, and they have transformers as its core. So what we can see that if we take, what is here in the table, I understand that, okay, this matrix often is not very interesting thing to look at, but let's look at, so we have different options for temporal point process models is THP, Neral-Hawkes, THP, RMTPP. And we have two options based on just convolutional neural networks without some this temporal point process magic, WaveNet and CCNN. And we can see that Kotick on average has a better N over 8 datasets for return time IEM and event time accuracy. And this, I suppose, because we selected the right complexity of the model. Because for recurrent type, it's problems with learning. And for transformers, there are too many parameters to learn. It's not an easy way to deal. So because of this, I suppose it's now better than other approaches. Also, I want to mention that right now, it's kind of problematic to learn these models because it takes a lot of time to learn them. And you can see it's training time in seconds per epoch for different approaches for 8 datasets. And you can see for some of them pretty big numbers, for example, transactions, Neral-Hawkes, a kind of crazy 14,000 seconds. Also not good for many other datasets. For our approach, the training time is on average okay, and is better than the results, the training time for approaches that has the closest metrics. We could say that we developed an efficient approach. And you can see that this dataset is practically not very big, like up to this transactions is the biggest one, yeah, is about 20 millions of events with 30,000 of sequences, but still it's kind of smaller than, for example, datasets used for modeling in natural language processing. I suppose we'll see more efficient models later, maybe with some adoption of techniques from NLP. And okay, this was only a brief introduction to this topic. There are many application areas that allow principled modeling in combination with neural networks based on temporal point process, for example, earthquake prediction, operations in the stock market, at clickstream data when we collect what users are doing. I suppose that we will see new works in this area. For example, it's not clear how we can cluster events, how we can cluster event sequences. Also for novel detection, change point detection, there are some works, but not many of them. And also, I suppose that we can try to take RL sync here and try to optimize interactions with users using this thing. Also, it's another source of how can we define self-supervised problem. And I suppose we will see some improvement in this area later. Other problems that's not covered, but I suppose interesting, is what we should do for causality discovery if we want to have processing of many sequences of events that occur in parallel. Also, what we can do if we know for sure that we have some missing events. For example, we are a bank and we see some transactions of a user, but we also we know that there are other banks and the user can have another card at another bank. How can we process this in a correct way? That's not clear, I think, for now, but I suppose we'll be able to do as well. So we now see that there is another mechanic based on another probabilistic approach to the process of advanced sequences. And we can build neural networks on top of that to provide kind of good performance. We have a nice combination of a theoretical model and modern neural networks. And I encourage you to try these approaches and to make your own contributions to this field, because I suppose it's a better way to look at this problem without ignoring some parts of it. So that's all for me. Okay, I'm finished almost in time. And I think that we have a QA session now.
Yes, thank you very much, Alexey, and thanks for your interesting talk. Dear colleagues, if you have any questions, please write them. And in the meantime, I will probably ask one or two questions. So, Alexey, my question is: so you have your model, and we know that, like in deep learning, some models are relatively, I would say, stable and easy to train, like for some image classifiers, and some models are a little bit more brittle, like probably scan type models or something like that. And for your model, is it like does it work out of the box, or are there any significant efforts needed to tune hyperparameters and so on?
Okay. We actually did this experiment. It's a very interesting question. And for many other models, it's really a problem that they are not very stable and they require a lot of time to tune. And given that training time is large, it can be a very big and hard process. For our approach, it's actually much easier, in my opinion, to make it work, maybe because of this intrinsic stability of convolutional neural network. So I would say that, okay, we need some more research on this because the area is narrower, but I hope we are close in a way to what we have in image processing, kind of common architectures, isn't it?
Okay, I see. And you mentioned here that you do these experiments on 8 data sets. So can you comment what type of data sets these are?
Yes, very good question. I will open my article shortly. And so basically, the main kind of data sets in this area is data sets related to retweets on kind of this. Each tweet is an event. It's easy to collect data from Twitter, so we can try to understand the dynamic of these tweeters in different ways. Also, there are other applications. The first idea is, for example, to consider something like financial transactions, another data set. Also, some purchases from retailers like Amazon. There is another Amazon data set. Another example that's often considered is question answering sites, where we have question like Stack Exchange. There is a famous Stack Exchange data set. We try to predict the next question or the next answer to a question. Another interesting application is LinkedIn. In this case, you try to predict the next switch of a job, which is an event in this sequence. And there are others, but I suppose it's enough for now. So they're kind of very diverse.
Yeah, that's a good overview, thanks. And I think that's what is interesting, that's quite diverse here. So that shows somewhat generality of your approach, probably. All right, I don't have any more questions myself, and colleagues are somewhat a bit silent today. I'm not sure, probably everyone is waiting for the holiday. Tomorrow we have a holiday in UAE, so non-working day. Probably that's the reason.
Oh.
I don't know. Okay. Thanks a lot, Alexei. Thanks again for your talk. Thanks everyone for coming to listen, and see you at next seminars. Thank you very much. Bye bye.
Okay, thank you for inviting me. Goodbye. Have a nice day.
You too. Bye bye.